Hello, I'm here to introduce you to the X-shooter Spectral Library and stellar population models, highlighting the near-infrared part of the spectrum of a stellar population which is ruled by cool evolved stars. The construction of a simple stellar population model is rather straightforward as it consists of three ingredients only: stellar evolution theory, an initial mass function, and a stellar spectral library. These ingredients are typically combined by this equation. The nuanced ingredients themselves make the population modeling difficult in practice, and the advancement to the near-infrared even more so due to the complex nature of very cool giant stars. We're presenting a new generation empirical stellar library and associated stellar population models. This spectral library has a moderate high resolution of around 10,000 and extends from near ultraviolet to near infrared. With its 830 stars, we will cover the entire HR diagram as extensively as possible and with an emphasis on these advanced stellar evolutionary stages. A special care was done to select red giant branch stars, asymptotic giant branch stars, long period variables among them, which are highlighted on the histogram. The need for updated optical to near-infrared stellar population models was highlighted, for example, in a study on both starburst galaxies by Zibetti et al. In 2013. These galaxies are characterized by insignificant ongoing star formation and a spectral energy distribution dominated by stellar populations formed in a recent, less than 2 gigayear-old burst. These galaxies should, by our understanding, have strong thermally pulsing AGB features in the near-infrared spectra. A few of those galaxies are shown here on the left. No strong features were detected. However, the stellar population models vary in the near-infrared spectral energy distributions because of the handling of cool evolved stars. For example, the thermally pulsing AGB heavy Marastan models and the light Brusual-Charlot models shown on the right. We're far from a complete understanding of some stellar evolutionary phases that strongly affect the near-infrared spectral energy distributions. Yet we need to include these stars into the stellar population models. Individual observed spectra of those stars are very varied in their near-infrared spectral energy distributions, so they cannot be used directly in the synthesis of galaxy spectra. An ideal stellar library should include spectra of individual variable stars observed over their pulsation cycles. In reality, the light curves and phases are generally not accurately known. Furthermore, the stellar parameters are not accurately known. In XSL stellar population modeling, we are using average spectra of static giants, oxygen-rich or carbon-rich thermally pulsing AGB stars pinned by broadband color. We rely on stellar evolutionary theory to dictate where RGB, early AGB, oxygen-rich or carbon-rich thermally pulsing AGB star should occur. Then we let empirical relations to tell us where an average spectrum of a star of a certain color should occur. XSL stellar population models do need to describe the reality. For one, we can describe the colors of early type galaxies from SDSS and 2MASS. Furthermore, we expand the model capabilities of fitting near-infrared indices of early type galaxies in red and starburst galaxies, which are shown in blue. The shaded area represents XSL models with different metallicities, with the spectral resolution going from 16 kilometers per second, which is the XSL original, to 228 kilometers per second. The black lines represent E-Mille-Spasti model predictions, with dotted dashed and solid lines representing the different metallicities. CO2.2, for example, is believed to be enhanced in younger stellar populations, possibly due to supergiant stars, although the models would state otherwise. However, neither the XSL or E-Mille models go to such young ages. It is now possible to perform in-depth studies of spectral features in the near-infrared. However, one needs to keep in mind that individual elemental abundance variations, velocity dispersion, wavelength shifts, signal-to-noise ratio, flux calibration, and initial mass function can influence the near-infrared spectral line indices. But the XSL will help us to bridge the optical and the near-infrared studies of intermediate and old stellar populations, clarify the role of evolved cool stars in stellar population synthesis, and create new possibilities in the near-infrared absorption line index studies. Thank you for listening, and don't hesitate to reach out and connect.